you for inviting me to present my work in this conference. So this is about estimation of finite population size by sequential sampling methods. I'd like to go through some overview. And so we are basically discussing here the mark recapture method. In mark, it is also known as capture tag release recapture. Here one first capture T items from the population and then tag them and then release them back in the population, and then collect another sample from the population and look until a certain number of tagged items are recaptured. And so here the number of tagged items that are to be recaptured is fixed in advance, but an important question is how one can decide this number S, and that's what precisely the topic of this talk. So we will adopt a purely sequential approach in estimating the required number of required optimal choice of S, and thereby arrive at an appropriate estimator of the population size. So in order to first define the probability distribution here, where S is fixed for now, then xi, it can be seen that xi, if it stands for the number of independent and identically distributed trials required to observe the ith tagged item, then xi follows a geometric distribution with the usual parameters. But since we want S tagged items, so x1 plus x2 plus xs, that is the total number of items that have to be observed, and then that is, if we call that y, then y has this mean and the variance. And then this is one of the most important expressions. So this is the estimate of the population size, and that is t times x bar s, and it has an estimated variance which is given by this. But now this, whatever estimator we got, so if we want to quantify the error in estimation, then we use a squared error loss function. And then if we want to define the risk, this is the risk, and if the expression for the risk will be this. And then if we want to bound the risk by a positive pre-assigned quantity, then we call that omega. So for that we have a fixed sample choice for that. Fixed size optimal choice for S is given by this. But if we want to do a minimum, if we want to minimize the risk instead of bounding the risk, so this bounded risk formulation was done by Mukhopadhyay and Bhattacharjee in 2018, and then recently Zhuang and Bhattacharjee we have formulated a minimum risk point estimation. So in that case we have the advantage of incorporating a cost in sampling, and then the risk of that will be given by this quantity, and then since we are minimizing the risk, the optimal choice for S will be given by this. Now whether it is bounded risk here, this expression, or for the minimum risk, in both cases P is involved in the choice of S, so S, the optimal choice for S, that is S star, remains unknown. So we adopt a sequential methodology, and the sequential methodology comes with a stopping variable. So here is the definition of the stopping variable that we will be using. So for the bounded risk, this is the stopping variable, and for the minimum risk, this is the stopping variable. Now so the way the stopping variable works is, for that I'll quickly go over an example and then I'll come back to those results. So suppose we have a jar of white beads, and then we don't know how many white beads are there. Now what we are doing, we took a handful of white beads and we happen to have 67 such white beads, and then we replace those 67 white beads by pink beads. And so in the entire population of beads we have some white and some pink, tagged, untagged, and then the entire box is shuffled. We pick one at a time until a pink bead is observed, and so we are this is the result of the simulation of the experiment that I am just describing. So here is the first tag, that means first pink bead is observed when we took 10 beads, and so we compute that quantity in the stopping rule. So this is one stopping rule. I will come back to this stopping rule later. This is one stopping rule. We will compute the quantity and see if the condition, that is S greater than this quantity, is satisfied or not. That is how the stopping rule is applied in practice. So let me go back to the problem again. So once we stop, so once this condition is satisfied, we will stop, and we have this data in our hand, and using that data we can get an estimate of the population size, and we can compute the risk, the ratio of the risks, optimal risk and the sequential risk, and the optimal risk is called risk efficiency. Now it can be shown that there are some optimal properties of this sequential procedure, and two of them are very important. One is asymptotic first order property and the asymptotic risk efficiency. So both these properties can be proved. We are just skipping the details here. Now, one thing is that this process of sampling could be very time consuming, so we thought of adopting an accelerated sequential procedure. In accelerated sequential procedure, we have an early stoppage by applying acceleration by considering this factor rho a fraction in the stopping rule. We have an early stoppage, but then once we stop, because of the early stoppage, we have to see what is the deficit. That here we have we are actually looking at the number of tagged items, so we have to see what is the deficit. The deficit, that is t minus t0, which is obtained from this equation. T is obtained from this equation, and t minus t0, that is the deficit. Then we have to do another quick sampling, like a batch sampling, to get this t minus t0 remaining required tagged items, and finally come up with the estimator of the population size. But here what we have done something different. The accelerated sequential also has some good properties, but if we think about the real convenience, the design of accelerated sequential sampling does not provide that, because the sampling is inherently one by one. We cannot do a batch sampling. So to adopt that, we have applied a hypergeometric distribution. We have taken the help of hypergeometric distribution and then maximum likelihood estimate for the number of items that should be collected in a batch, so that we have a maximum probability of observing the required number of remaining tagged items. And the equation for that is given by this. This is the equations. So this is a preliminary estimate of the population size, and then final estimator of the population size will be given by this. Let us go through some quick simulations. So here is the result of the minimum risk point estimation. Here we have different values of n, and then different values of tagged items, and then we have S star, then S bar, and then so our estimated population size turns out to be very good. And these are, so the modification of the accelerated sequential procedure that we have discussed, that's called that is, we are calling it practical accelerated sequential, and the results for that are also given for different values of rho. So results are very consistently good throughout, and there are some first order and second order properties that we can see here in the estimation. And then we also show a little bit of result on the bounded risk point estimation. So here was the illustration of the data. So after applying all this procedure, we saw that the box had 478 beads. So with that, I'd like to just conclude with this final remark, that this table actually shows the efficiency of the earlier procedure by Mukhopadhyay Bhattacharya and the Zhuang Bhattacharya, recently proposed Zhuang Bhattacharya procedure. And in all the cases, the Zhuang Bhattacharya procedure actually is more efficient. And so these are some ongoing research on these topics, and I would like to thank my co-authors for all these different projects, Dr. Nitesh Mukhopadhyay, Dr. Yan Zhuang, and Dr. Ivar Silva. So thank you for your attention.